Hello everyone, hope you're doing well. Today we're going to start with a new unit. It's about optics, and the first lesson in this unit is about lenses. We took it last year. It's not a new lesson. We don't have new concepts in this lesson. We will start with a revision about the bodies. Bodies can be divided into three types. We have the transparent bodies, we have the translucent, and we have the opaque ones. The transparent bodies allow the light to pass through. That's why we can see through them. Translucent are materials that allow a slight passage of light. It's like the ones used in the windows of bathrooms or maybe office in a company. And the third one, which is the opaque will not allow any passage of light. Example, the cardboard, the wood, the wall, plastic, very thick plastic. The transparent, it's like the glass or the transparent plastic. As a definition, what are thin lenses? A thin lens is a transparent and homogeneous medium. Homogeneous means one face. It's limited by two surfaces. One of these two surfaces, which is called the face also, must be spherical, while the other must be spherical or plane. What's the meaning of spherical and what's the meaning of plane? We will talk about later on. Lenses can be divided into two types, if you can remember them. We have the converging lenses and we have the diverging lenses. The type of lens can be recognized by its shape. First, we look at the converging lens. The converging lens has thin edges and thick center, while the diverging lens has thin center and thick edges. As you can observe over here, the edges are thick compared to that of the center, while in the converging lens the center is thick and the edges are thin. So converging lens and diverging lens are the opposite of each other. We have three different types of converging lens and three different types of diverging lens. Over here we have a spherical face and another spherical face. We have a plane face and a spherical face. We have a spherical face and another spherical face. This is what we were talking about in the definition. We have spherical face, we have spherical, we have plane, and spherical. So this is the way we recognize converging lens by looking at its shape. The edges must be thin while the center must be thick. While in a diverging lens, the center must be thin while the edges must be thick. This looks like an apple, so remember, an apple shape means a diverging lens. We have the names of these lenses. You must know these names. So for converging lenses, when I have two spherical shapes or two spherical faces, we call it double convex. When I have a plane and a spherical shape, we say plano convex, because converging lenses are also called convex lenses. Diverging lenses are also called concave lenses. In this one we have the spherical and spherical, but they are right parallel to each other. We have the converging meniscus, it's called. In this one we have double concave. So this one is called double convex. This one is called double concave. This is called plano convex. So this one must be plano concave. This is called converging meniscus. So this one must be diverging meniscus. The symbol of a converging lens, we have the symbol must be segment, whose extremities must be arrows, as you can observe, because the converging collects the light. In the diverging lens, we must have a segment and arrows that are in the opposite direction, because diverging lens spreads the light out. So the symbol can supply you with more information about the lens. We can also know the type of the lens by the size of the object. The converging lens magnifies the object, while the diverging lens diminishes the object. As you can observe over here, we have a lamp in front of the converging lens. The lamp magnifies. Okay, this is the image of the lamp. This is what the eye sees. While in the concave lens, we have the object, which is the lamp. Through a concave lens, which is a diverging lens, the eye will see its shape smaller than the normal one. The effect on light. We have the converging lens will collect the light through one point. So if the beam of light passes the parallel rays into the converging lens, it's going to collect at one point. So we call them the emergent rays. Okay, these are called emergent rays. It approaches the optical axis. Do you remember what's the optical axis? It's one of the characteristics of the converging lens, where we locate a perpendicular axis into the center of the lens. Okay, the diverging light, we have the source of light emits parallel rays. When it hits these emergent rays hit the diverging lens, it's going to spread out, so it deviates away from the optical axis. This is how we can differentiate also between a converging lens and a diverging lens. The concave surface curves inward. This is about the name. How did they get the names of the lenses? The concave surface curves inward. This is in diverging lens, while in converging lens, which is convex surface, it bulges out. We have the concave lens causes light rays to spread apart, as we said, diverge, while in convex lens, which is the converging lens, it causes the light rays to meet or converge at one point. The concave mirror is a type of we have concave mirrors and convex mirrors. We are not going to deal with them this year, so it's just extra information. It causes light rays to meet or converge, while the convex mirror causes light rays to spread apart or diverge. This one is used in the roads, so that the cars can or the drivers can tell if there's a car coming towards it or not. The position of the object focus and the image focus, do you remember them? We have the converging lens and we have the diverging lens. These are the elements of the lens. We have the optical axis, which we said that it's a parallel axis, it's a perpendicular axis to the lens. It passes through its midpoint, which is called the optical center. We also have it in the diverging lens. So we have the optical center, it's the intersection of the optical axis and the lens itself. This is also called the principal axis. We have 2 points, F and F prime. F is the object focus and F prime is the image focus. In the converging lens, first F and F prime must be symmetric to each other with respect to O. So F prime is the symmetric of F with respect to O. And also over here, F prime is the symmetric of F with respect to O. So O is the midpoint of F, F prime. So we can say that FO, F prime is in a converging lens, while F prime OF is in a diverging lens. We have something called the focal length. The focal length, it's the distance between the optical center of the lens and its image focus F prime, which is over here O F prime. This is the positive sense, so O F prime must be positive. This is called the focal length and it's symbolized by the letter F. While in a diverging lens, it's O F prime in this direction and the positive sense is in the opposite direction. That's why O F prime will be negative in diverging. So now we have to represent a converging lens. We have the focal length. We said the focal length is the distance between the optical center O and the image focus F prime. In the representation of a diverging lens, we have the focal length, which is OF prime. It's the distance between the optical center O and the image focus F prime. Let's go back to a converging lens. In the converging lens, we have F O F prime, while in a diverging lens, we have F prime O F. As you can observe, the optical center cut the lens into two equal parts. We have them 3 centimeters upward and 3 centimeters downward. Now the behavior of specific rays. We have the first case where any ray passing through the optical center of the lens, it continues its path without deviation. So over here we have the ray passing through the optical center of a converging lens. It continues undeviated, and in a diverging lens also, any ray passing through the optical center of a diverging lens, it continues undeviated. So any ray passing through the optical center will emerge without any deviation. Any ray parallel to the optical axis of a lens, it emerges passing through the image focus of a converging lens. So any ray parallel to the optical axis, when it hits the lens at a specific point, it's going to collect at the image focus F prime. Okay? Now in a diverging lens, any parallel ray to the optical axis, it emerges seeming to come out from image focus F prime. So we are going to make something called prolongation. I already mentioned this word in class. We said the elongation is forward, while the prolongation is backward. We have over here, when the parallel ray hits the diverging lens, it's going to spread out. How much should we spread it out? This thing depends on the image focus of the diverging lens. If the image focus is over here, it's going to spread out. We link F prime with the angle or the point of incidence over here, and we have 2 points, so we can make a straight line. Okay, so it seems to come out from image focus F prime. If the image focus F prime over here, we link F prime with the incident point over here. Now the third case, when we have a ray passing through the object focus of a converging lens, when it hits the lens, it continues parallel. It's the opposite of this case. When the ray comes parallel, it collects at F prime. But when the ray comes passing through object focus, it continues parallel. The fourth case for a diverging lens, when the ray passes as if coming into object focus of the diverging lens, it continues parallel. So it's the opposite of this case, where we have a parallel ray spreads out as if coming out from image focus F prime, while in this case, if the ray is passing as if coming into object focus F, it will continue parallel. The previous ones are called specific cases. Now the converging lens, how does it act? If a beam of light is parallel to the optical axis and is directed to the lens, the light converges at the image focus F prime. This is called the focal length. It's the distance between optical center and the image focus F prime. This is called the principal axis, we said. The diverging lens, when a beam of light, the beam of light must be symbolized by 2 rays, one above the optical axis and one below the optical axis. Okay, what is a beam of light? A beam of light emits several rays at the same time. So when the beam of light emits parallel rays to the principal axis of a diverging lens, these parallel rays will spread out as if coming out from the image focus F prime, and we said that the focal length of this lens will be from the optical center into the image focus F prime. So as a summary for the lesson, we have the lenses are divided into converging and diverging lenses. We can specify the type of the lens by the edge, which means the shape, the rays, the optical axis and its characteristics, or by the image itself. The edge is thin compared to its body, where we have thin edges and thick center in the converging. In the diverging, it's the opposite. We have thick edges and thin center compared to its body. The rays converge in a converging lens, which is also called convex lens, and meet at one point, as you can observe over here. They are meeting at one point. The direction of light is from right to left in this case, and here also from right to left. So we have to take care about the direction of the light. It might be from right to left or from left to right. So in diverging lens it spreads out, which is also called concave lens. The optical axis, we have the optical center for both. In the converging lens it must be FO, F prime. In a diverging lens it must be F prime OF. The lens will be symbolized by a segment that has at the top arrows in a converging lens, and the opposite in a diverging lens, as if it's symbolizing how the rays come out from this lens. The focal length is the distance between the optical center and the image focus of the lens. In a converging lens it's positive, in a diverging lens it's negative. This figure shows how the particular rays move through the converging lens and through the diverging lens. In a converging lens we have the parallel ray collects at F prime. Any ray passing through the optical center continues undeviated, while in the third case, when it passes through F, it emerges parallel to the optical axis, which is the opposite of the first case. These are called particular rays. In the diverging lens, the parallel ray diverges out as if coming out from the image focus F prime. The second case, which is the ray passing through the optical center, continues undeviated, and the third ray, which seems to come into the object focus, continues parallel. So these are called particular rays, three cases. Now we might have any ray that comes into the converging lens, we make it converge into the optical axis. And in this case, any ray coming into the diverging lens, we make it deviate away from the optical axis a little bit. So this is the summary of this lesson. It's a very easy lesson. It's the introduction for the next one. We still have one and only one lesson, which is the formation of images. It's related to lenses also, and you will be done with physics. Hope you enjoy this lesson. Stay safe, and thank you. Missing you lots, my dear.